Hello there. I'm so glad you found your way here tonight. Wherever you are in the world right now, allow yourself to settle into this shared moment of stillness. Let the noise of the day fade away. Let your thoughts grow quiet, like the gentle rhythm of waves lapping against a distant shore. Right now, as you listen to these words, something extraordinary stretches across most of our planet. A vast blue world of mystery and wonder. The ocean covers more than 70% of Earth, yet we have explored less than 5% of its depths. Entire mountain ranges, hidden valleys, and creatures beyond imagination wait in the darkness below. Tonight we journey into the deep, into the quiet realm of the ocean itself. A world of glowing creatures, underwater waterfalls, and secrets older than the first forests on land. We will explore how the ocean shapes our climate and our weather. How life thrives in places where no sunlight ever reaches. How ancient sharks patrolled these waters before trees existed on land. And how the sea holds treasures, mysteries, and wonders we are only beginning to understand. All of it waiting to be shared in the stillness. Tonight, let's drift off together while exploring over 100 soothing facts about the ocean. There's no rush here. No test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the vast waters that embrace our world. Either way, this space is for you. There is something deeply calming about contemplating the ocean. Every wave carries the memory of countless journeys across the globe. Every drop of water has been part of clouds, rivers, and ancient seas, stretching back billions of years. You are connected to this story more than you might realize. The water in your body was once part of the ocean. The air you breathe was shaped by tiny creatures drifting in sunlit waters. The rhythm of the tides is written into the very fabric of life on Earth. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow. And let the weight of the day drift away like foam dissolving into the endless blue. The ocean is patient beyond measure. Currents circle the globe for centuries without rest. Mountains rise from the seafloor over millions of years. Creatures evolve in darkness, adapting to pressures that would crush any machine we have built. And yet, within all that steadiness, there are sudden bursts of wonder. Volcanic islands, born overnight. Whales singing songs that travel across entire ocean basins. Bioluminescent displays that turn the midnight waters into fields of living stars. Tonight, we will wander through this magnificent underwater world. We will meet the forces that shape the seas and discover creatures that defy our imagination. But there is no hurry. The ocean has been here for 4 billion years. It can wait a little longer while you rest. Let us begin with the vastness of our blue planet. The ocean covers more than 70% of Earth's surface. When viewed from space, Earth appears as a blue marble, and that stunning color comes from the vast expanse of water that dominates our planet's surface. The ocean stretches across more than 360 million square kilometers, dwarfing every continent and landmass combined by a significant margin. This immense body of water is not a single uniform sea, but a connected system of 5 major ocean basins that flow into one another without true boundaries. The sheer scale of the ocean means that most life on Earth exists within its waters rather than on dry land, making it the planet's primary habitat. Sailors and scientists have spent centuries mapping its coastlines and charting its depths, yet the open ocean remains largely a mystery waiting to be explored. The surface we see is only the beginning, hiding depths that plunge kilometers below. The blue world is the true face of our planet, a realm of water that defines Earth's identity in the cosmos. We have explored less than 5% of the ocean floor. Despite centuries of maritime voyages and decades of modern oceanography, the ocean floor remains largely unseen by human eyes or instruments, hidden beneath kilometers of saltwater. The crushing pressures, total darkness and vast distances make deep-sea exploration far more challenging than sending probes into outer space. Most of our detailed maps of the sea floor come from satellite measurements of surface gravity, which can only infer the shapes of features far below. Submersibles and remotely operated vehicles have visited isolated spots on the seafloor, but these represent tiny pinpricks on an enormous canvas that remains largely unexplored. Entire mountain ranges, valleys, and ecosystems lie hidden beneath the waves, waiting for future explorers. The deep ocean may hold answers to questions about the origins of life and the limits of biology. We know more about the surface of Mars than we do about the seabed just a few kilometers from shore. The deepest point in the ocean is deeper than Mount Everest is tall. The Mariana Trench, located in the western Pacific, plunges to a depth of nearly 11 kilometers at a spot known as Challenger Deep, the lowest point on Earth's surface. If Mount Everest were placed at the bottom of this trench, its summit would still be more than a kilometer beneath the waves, completely submerged. The pressure at this depth exceeds 1,000 times the atmospheric pressure at sea level, crushing anything not specifically engineered to withstand such forces. Yet even here, life persists in forms adapted to the extreme environment in ways scientists are still trying to understand. Small amphipods, shrimp-like creatures, scavenge on organic debris that drifts down from above through the water column. The journey to the bottom takes hours in a specialized submersible, passing through layers of ever-increasing darkness and cold. This deepest point reminds us that our planet's true extremes lie not on mountain peaks, but in the silent darkness beneath the sea. More people have walked on the moon than visited the deepest trench. As of recent counts, a dozen astronauts have set foot on the lunar surface, while only a handful of brave explorers have descended to the bottom of the Mariana Trench. The challenges of deep-sea exploration are immense: crushing pressure, total darkness, and the need for life support systems that can endure for hours in complete isolation. Building a craft capable of surviving these conditions is an engineering feat comparable to designing a spacecraft. The first successful descent to Challenger Deep occurred in 1960, when Jacques Piccard and Don Walsh reached the bottom in the bathyscaphe Trieste. Since then, only a few manned expeditions and a small number of robotic missions have followed. The rarity of these visits underscores just how inaccessible the deep ocean remains. In many ways, the abyss is as remote and alien as the surface of another world. The ocean holds about 97% of all water on Earth. Nearly all the water on our planet exists in the ocean, with only a tiny fraction found in ice caps, groundwater, rivers, lakes, and the atmosphere around us. This vast reservoir of saltwater shapes global climate, drives weather patterns, and sustains the majority of life on Earth in countless ways. Fresh water, the kind we drink and use for agriculture, represents less than 3% of the total supply, and much of that is locked in glaciers or deep underground. The ocean's dominance in the water cycle means that evaporation from its surface feeds massive clouds that eventually rain on continents far inland from any coastline. Without the ocean, the land would be a barren desert, and the atmosphere would be radically different from what sustains us today. The saltiness of seawater comes from minerals dissolved over billions of years, giving the ocean its distinctive chemistry that supports unique forms of life. Earth is, in essence, an ocean planet with scattered islands of dry land. There are mountain ranges beneath the sea longer than any on land. Beneath the waves lies a system of mid-ocean ridges that stretches around the globe like the seams on a baseball, spanning over 65,000 kilometers in total length. These underwater mountain chains are the longest geological features on Earth, dwarfing the Himalayas, the Rockies, and the Andes, combined by a significant margin. They form along the boundaries where tectonic plates pull apart, allowing molten rock to rise from the mantle and solidify into new ocean floor that pushes outward. The peaks of some ridges rise several kilometers above the surrounding seabed, though they rarely break the surface except in special locations. Iceland is one famous exception, an island born where the mid-Atlantic ridge emerges above the waves in dramatic volcanic fashion. The mid-ocean ridges are sites of constant volcanic activity, earthquakes, and hydrothermal venting that support unique ecosystems. These hidden ranges are the engines of plate tectonics, continuously reshaping the geography of our planet over millions of years in ways that affect all life on Earth. The Mid-Atlantic Ridge stretches for over 40,000 miles. Running down the center of the Atlantic Ocean like a jagged spine, the Mid-Atlantic Ridge is one of the most prominent features on Earth's surface, though almost entirely hidden from view. This immense mountain chain marks the boundary where the North American and Eurasian plates pull apart from the South American and African plates. As the plates separate at a rate of a few centimeters per year, magma rises to fill the gap, creating new oceanic crust. The ridge extends from the Arctic Ocean near Iceland all the way to the Southern Ocean near Antarctica. Along its length, the seafloor is marked by volcanic peaks, deep rift valleys, and hydrothermal vents teeming with life. The Mid-Atlantic Ridge is a living laboratory for understanding plate tectonics and the birth of new ocean floor. Its existence was one of the key discoveries that confirmed the theory of continental drift. Most of Earth's volcanic activity happens underwater. While dramatic eruptions on land capture headlines and imaginations, the majority of volcanic activity on our planet occurs quietly beneath the ocean's surface. Mid-ocean ridges are sites of nearly continuous volcanic eruption as magma wells up to create new seafloor. Thousands of seamounts, underwater volcanoes that do not break the surface, dot the ocean floor in every basin. Many of these eruptions go unnoticed because they occur far from coastlines and at depths where no one can see them. The water pressure at depth can suppress explosive eruptions, causing lava to ooze out slowly and form pillow-shaped formations as it cools. Occasionally, submarine eruptions are powerful enough to create short-lived islands of pumice or even new permanent landmasses. The ocean hides a geological fury that quietly reshapes our planet, hidden from sight, but never truly still. New islands can be born from underwater volcanic eruptions. When a submarine volcano erupts with enough force, the accumulated lava and ash can build up above the waterline, creating a new island seemingly overnight that captures global attention. These volcanic islands are often unstable at first, subject to erosion by waves and collapse as the underlying rock settles over time. Some survive and grow into permanent landmasses, eventually becoming home to unique ecosystems with plants and animals found nowhere else. The Hawaiian Islands began this way, rising from hotspot volcanism over millions of years to form the chain we know today. More recently, the island of Surtsey emerged off the coast of Iceland in the 1960s, providing scientists with a rare opportunity to study primary ecological succession from barren rock. other nascent islands have appeared in places like Tonga and Japan, drawing global attention before sinking back beneath the waves. The birth of an island is a reminder that our planet's surface is never finished, always in the process of creation and destruction shaped by forces deep within the Earth. Some underwater volcanoes rise higher than mountains on land. Measured from base to summit, several seamounts exceed the height of the tallest continental mountains. Mauna Kea in Hawaii, for example, rises over 10,000 meters from the ocean floor, making it taller than Everest when measured this way. Many seamounts remain entirely submerged, their peaks thousands of meters below the surface yet still towering over the surrounding abyssal plains. These underwater mountains create unique habitats where currents deflect upward, bringing nutrients and supporting diverse ecosystems. Fish, corals, and other organisms cluster around seamounts in densities far higher than the surrounding deep sea. The sheer number of seamounts, estimated at well over 100,000 worldwide, means the ocean floor is anything but flat. These hidden giants are monuments to the volcanic forces that continuously shape our planet. Seamounts also serve as navigational waypoints for migratory species crossing vast oceanic distances. The ocean floor is constantly being created and destroyed. At mid-ocean ridges, new oceanic crust forms as magma rises from below and solidifies, pushing older crust outward toward the continents in a continuous geological conveyor belt. At the same time, at subduction zones around the Pacific Rim and elsewhere, older oceanic crust dives beneath continental plates and is recycled back into the mantle deep within the Earth. This process means that the ocean floor is geologically young compared to the continents, with no seafloor older than about 200 million years anywhere on Earth. The cycle of creation and destruction drives plate tectonics, earthquakes, and volcanic activity around the world, shaping the landscapes we inhabit. It also means that the ocean basins are constantly changing shape over geological time as continents drift and collide. Oceans open and close as continents drift, a dance that has repeated many times over Earth's 4.5 billion year history. The seabed beneath the waves is not a permanent feature, but a transient surface, perpetually renewed and consumed by forces deep within the Earth that never rest. Entire underwater canyons rival the Grand Canyon in scale. Submarine canyons are deep valleys carved into the continental shelf and slope, often extending from near the coastline down to the abyssal plain. The Monterey Canyon off California, for instance, is deeper and longer than the Grand Canyon, though it lies hidden beneath the Pacific. These canyons were formed by a combination of tectonic activity, sediment-laden currents called turbidity flows, and the erosive power of rivers when sea levels were lower during ice ages. They serve as channels that funnel sediment, nutrients, and organic material from shallow waters to the deep sea. Many canyons support rich ecosystems, providing shelter and feeding grounds for fish, invertebrates, and marine mammals. The complexity of submarine canyons rivals that of any landscape on land, yet they remain largely unseen. These hidden gorges are among the most dramatic features of the ocean floor. There are lakes and rivers flowing at the bottom of the sea. Deep on the ocean floor, pools of extremely salty water known as brine pools collect in depressions, forming distinct lakes beneath the sea. These brines are so dense that they do not mix easily with the surrounding seawater, creating visible boundaries that look remarkably like shorelines viewed from above. Some brine pools even have waves rippling across their surfaces when disturbed by currents. In certain areas, denser water flows along the seabed in channels that resemble rivers, complete with banks and meanders. The water in these submarine rivers is often rich in dissolved minerals and can be toxic to most marine life. creatures that venture too close may be stunned or killed by the harsh chemistry. These underwater lakes and rivers are among the strangest features on our planet, hidden realms where familiar landscapes take on an alien form. Brine pools on the ocean floor are so salty, most life cannot survive in them. Brine pools form when ancient salt deposits dissolve into seawater, creating concentrations of salt several times higher than normal ocean water. The resulting brine is so dense that it settles into depressions on the seafloor, forming distinct pools with their own ecosystems. The high salinity creates an environment toxic to most marine organisms, yet some specialized bacteria and archaea thrive in these extreme conditions. Around the edges of brine pools, unique communities of mussels, tube worms, and other creatures feed on the chemicals and microbes that flourish there. For most fish and invertebrates, however, entering a brine pool means certain death. The sharp boundary between the pool and the surrounding water can be so clear that it looks like an underwater beach. These toxic lakes are reminders that the ocean contains many hidden dangers alongside its wonders. Underwater waterfalls can be taller than any waterfall on land. Beneath the ocean's surface, dense cold water sometimes plunges over underwater cliffs in cascades that dwarf any terrestrial waterfall. These submarine waterfalls are invisible from the surface, occurring where differences in water density cause colder or saltier water to sink rapidly. The Denmark Strait between Iceland and Greenland is home to the largest known underwater waterfall, where cold Arctic water drops nearly 3.5 kilometers as it flows southward. The volume of water involved is staggering, many times greater than all the rivers on Earth combined. These hidden falls play a crucial role in global ocean circulation, driving the thermohaline conveyor that distributes heat around the planet. The energy released as the water descends helps mix nutrients and oxygen through the deep ocean. These colossal cascades are among the most powerful, yet least visible forces shaping our seas. The Denmark Strait Cataract plunges more than 2 miles underwater. Located between Iceland and Greenland, the Denmark Strait Cataract is the world's largest known underwater waterfall. Cold, dense water from the Arctic sinks over an underwater ridge and plunges downward for over 3 kilometers before spreading across the ocean floor. The volume of water flowing over this cataract is estimated at several million cubic meters per second, far exceeding any river or surface waterfall on Earth. This massive flow is a key part of the Atlantic meridional overturning circulation, which carries warm tropical water northward and cold deep water southward. Changes to this flow could have significant impacts on climate in Europe and beyond. The cataract is invisible from the surface, detectable only through careful measurements of temperature, salinity, and current speed. It is a testament to the hidden power that moves through the ocean depths. The ocean produces more than half of the oxygen we breathe. While forests are often called the lungs of the Earth, the ocean actually produces the majority of the oxygen in our atmosphere. Tiny photosynthetic organisms called phytoplankton drift in sunlit surface waters, converting carbon dioxide and sunlight into oxygen and organic matter. These microscopic plants are so abundant that their collective output exceeds that of all terrestrial forests combined. Phytoplankton also form the base of the marine food web, supporting fish, whales, and countless other creatures. Their productivity varies with the seasons and is influenced by temperature, nutrients, and ocean currents. When conditions are right, phytoplankton blooms can be so large they are visible from space. Without the ocean's oxygen production, the atmosphere as we know it could not exist. Every second breath you take is a gift from the sea. Tiny phytoplankton are responsible for much of Earth's oxygen production. Phytoplankton are microscopic organisms, often single-celled, that live in the upper layers of the ocean where sunlight penetrates. Like plants on land, they use photosynthesis to convert carbon dioxide and water into sugars, releasing oxygen as a byproduct. Despite their tiny size, their sheer numbers mean they collectively produce a significant share of the world's oxygen. They also absorb carbon dioxide, playing a crucial role in regulating the planet's climate. Phytoplankton populations can fluctuate dramatically, depending on nutrient availability, temperature, and the presence of grazers like tiny zooplankton. When conditions are favorable, they reproduce explosively, turning vast stretches of ocean green or turquoise. These unassuming organisms are the invisible engines that keep our planet's atmosphere breathable. Their contribution is immense, yet they are too small for the naked eye to see. The ocean absorbs about a quarter of the carbon dioxide we release. As humans burn fossil fuels and clear forests, vast quantities of carbon dioxide enter the atmosphere, contributing to global warming. The ocean acts as a giant sponge, absorbing roughly a quarter of these emissions and helping to slow the pace of climate change. Carbon dioxide dissolves into surface waters and is gradually transported to the depths by sinking currents and biological processes. While this absorption has buffered some of the worst effects of greenhouse gas emissions, it comes at a significant cost to marine ecosystems. The dissolved carbon dioxide reacts with seawater to form carbonic acid, lowering the ocean's pH in a process known as ocean acidification. This change in chemistry threatens corals, shellfish, and other organisms that build calcium carbonate structures, putting entire food webs at risk. The ocean's role as a carbon sink is a double-edged sword, offering temporary relief but accumulating long-term harm that will affect generations to come. Ocean currents act like giant conveyor belts circling the globe. Beneath the surface, powerful currents transport water around the world in a continuous loop known as the thermohaline circulation, often called the global ocean conveyor belt. Warm surface water moves from the tropics toward the poles, where it cools, becomes denser, and sinks into the deep ocean. This cold, dense water then creeps slowly along the ocean floor toward the equator, before eventually rising again to complete the cycle. The journey of a single parcel of water can take 1,000 years or more. This circulation distributes heat, nutrients, and dissolved gases across the planet, influencing climate on every continent. Changes to the conveyor belt, such as those caused by melting ice, could have dramatic effects on weather patterns. The ocean's currents are the planet's hidden circulatory system, quietly regulating conditions for life. A single drop of water may take 1,000 years to complete one circuit. The global ocean conveyor belt moves water so slowly that a molecule starting in the North Atlantic may not return to the surface for centuries or even millennia. Along the way, it sinks to the deep ocean, travels along the seafloor to the Southern Ocean, rises in the Indian or Pacific basins, and eventually makes its way back to where it started. This immense timescale means the deep ocean contains water that last saw sunlight during the medieval period or earlier, carrying the signature of past climates. The slow pace of this circulation has important implications for climate, as it determines how quickly the ocean can absorb heat and carbon from the atmosphere. Changes happening now may not fully manifest in the deep ocean for generations, making the consequences of our actions long-lasting. The patience of ocean currents is measured not in human lifetimes but in the long rhythms of planetary history. Each drop of seawater is on an epic journey we can scarcely imagine, connecting eras across time. The Gulf Stream carries more water than all the rivers on Earth combined. Flowing northward along the eastern coast of North America, the Gulf Stream is one of the most powerful ocean currents on Earth. It transports warm tropical water toward Europe, releasing heat into the atmosphere, and giving Western Europe a climate far milder than its latitude would otherwise suggest. The volume of water carried by the Gulf Stream is staggering, estimated at tens of millions of cubic meters per second. This dwarfs the combined flow of every river on the planet, including giants like the Amazon, the Nile, and the Mississippi. The current is so strong and well-defined that it creates visible boundaries between warm blue Gulf Stream water and cooler green water on either side. Sailors have relied on the Gulf Stream to speed their voyages for centuries. This mighty river within the sea is a lifeline for climate and commerce alike. Ocean currents help regulate temperatures on distant continents. By transporting warm water from the tropics toward the poles and cold water in the opposite direction, ocean currents have a profound effect on regional climates far inland. Western Europe enjoys mild winters despite lying at the same latitude as Labrador, thanks to the heat released by the Gulf Stream and its extensions. Conversely, cold currents along the western coasts of continents can create cool, foggy conditions, even in otherwise sunny regions. The mixing of warm and cold waters influences where fish congregate, where storms form, and how much rain falls on nearby land. Changes in ocean circulation can shift these patterns, sometimes with dramatic consequences for agriculture and ecosystems. The ocean's currents are invisible threads, connecting distant shores, weaving together the climate of our planet. What happens in one ocean basin can ripple across continents. The tides are pulled by the gravitational dance of the moon and sun. Twice each day, coastlines around the world experience the rise and fall of the tides, a rhythm set by the gravitational pull of the moon and, to a lesser extent, the sun. The moon's gravity tugs on the ocean, creating a bulge of water on the side of Earth nearest the moon, and another bulge on the opposite side due to inertia. As Earth rotates beneath these bulges, coastal areas pass through high and low tides in a predictable pattern that sailors and fishermen have relied upon for millennia. When the sun, moon, and Earth align during new and full moons, their combined gravitational pull creates especially strong spring tides. When the sun and moon are at right angles, their pulls partially cancel, resulting in gentler neap tides. Tidal ranges vary enormously depending on local geography, from centimeters in some seas to over 10 meters in places like the Bay of Fundy. The tides are a constant reminder of our planet's place in the cosmic dance of gravity, shaped by celestial neighbors. King tides can raise sea levels several feet higher than normal. King tides are exceptionally high tides that occur when the gravitational alignments of the moon and sun are at their most favorable, often during new or full moons when the moon is at its closest point to Earth. These tides can push water several feet above normal high tide levels, flooding low-lying coastal areas and offering a preview of what rising sea levels may look like in the future. King tides expose the vulnerability of coastal infrastructure, from roads and storm drains to buildings and wetlands. They can cause saltwater intrusion into groundwater, damage property, and disrupt ecosystems that depend on predictable tidal patterns. Scientists and planners use king tide events to model the impacts of climate-driven sea level rise. While king tides are natural and temporary, they are a powerful reminder of the ocean's influence on our shores. The reach of the sea is never truly fixed. Tsunamis can travel across entire oceans at jet speed. Triggered by underwater earthquakes, volcanic eruptions, or landslides, tsunamis are waves of tremendous energy that can race across the open ocean at speeds exceeding 700 kilometers per hour. As fast as a commercial jet. In the deep ocean, these waves may be only a meter or so high and pass unnoticed beneath ships sailing above. However, As they approach shallow coastal waters, the energy is compressed, causing the waves to slow down and grow to devastating heights that can overwhelm entire communities. A tsunami generated on one side of the Pacific can reach distant shores within hours, giving little time for warning and evacuation of coastal populations. The destruction caused by tsunamis throughout history has shaped coastal cultures and inspired early warning systems designed to save lives. The speed of these waves is comparable to that of a commercial jet, making the ocean a highway for disaster that crosses thousands of kilometers. The sea can transform from calm to catastrophic in the time it takes to cross a continent. The tallest wave ever recorded by instruments was over 30 meters high. In the open ocean, wind-driven waves rarely exceed 10 meters, but extreme conditions can produce monsters that tower far higher. The tallest wave ever recorded by a scientific instrument measured over 30 meters, roughly the height of a 10-story building. Such waves typically form when powerful storms generate sustained high winds over long stretches of open water, allowing wave energy to build. In rare cases, waves can combine constructively, stacking on top of one another to produce what are known as rogue waves. These giants appear suddenly and can be far larger than surrounding seas, posing extreme danger to ships. Historical accounts of massive waves were once dismissed as sailors' tales, but modern instruments have confirmed their existence. The ocean's surface, so often calm and gentle, can transform without warning into a wall of water. Rogue waves can appear suddenly without warning in the open sea. Rogue waves, also known as freak waves or monster waves, are unusually large ocean waves that appear seemingly out of nowhere. They can be more than twice the height of surrounding waves, rising suddenly before dissipating just as quickly. For centuries, tales of ships struck by towering walls of water were attributed to exaggeration, but scientific measurements have confirmed that rogue waves are a real phenomenon. They form when wave energy from different directions converges, constructively interfering to create a wave far larger than any individual component. Strong currents flowing against the prevailing wave direction can also steepen waves dramatically. Rogue waves have damaged large vessels and offshore platforms, sometimes with catastrophic consequences. The unpredictability of these waves makes them one of the ocean's most feared hazards, a reminder that the sea is never fully tamed. Storm surges can raise sea levels higher than a house. When a powerful storm approaches the coast, low atmospheric pressure and strong onshore winds can push a mound of water ahead of the storm, raising sea levels far above normal. This storm surge can add several meters to the height of the tide, flooding coastal areas that would otherwise remain dry. The deadliest effects of many hurricanes and typhoons come not from wind, but from the wall of seawater that rushes inland. Low-lying regions can be inundated within minutes, sweeping away buildings, roads, and lives. The shape of the coastline influences the severity of the surge. Funnel-shaped bays can amplify the effect dramatically. Storm surges are a leading cause of fatalities in coastal storms and a major concern as sea levels rise. The ocean's power to reshape the land is never more evident than in the fury of a storm. The Pacific Ocean is larger than all continents combined. Stretching from the Americas to Asia and from the Arctic to the Southern Ocean, the Pacific is by far the largest body of water on Earth. Its surface area exceeds 160 million square kilometers, making it larger than all the land on our planet put together. The Pacific is so vast that it contains more than half of the world's free water and hosts thousands of islands scattered across its expanse. Its depths include the Mariana Trench, the deepest point on Earth, as well as countless seamounts and underwater plateaus. The Pacific Ring of Fire marks its edges, a zone of intense volcanic and seismic activity. Early European explorers named it for its seeming calmness, a misnomer given its powerful storms and turbulent history. The Pacific's sheer scale makes it a defining feature of our planet. The Atlantic Ocean was born from a splitting supercontinent. Around 200 million years ago, the supercontinent Pangaea began to break apart, and as its fragments drifted away from one another, a new ocean filled the widening gap between them. This growing basin became the Atlantic Ocean, which continues to expand today as the Mid-Atlantic Ridge pushes the Americas away from Europe and Africa at a rate of several centimeters per year. The Atlantic is the second largest ocean, extending from the Arctic to the Southern Ocean and separating the Old World from the New. Its waters have been highways for exploration, trade, and cultural exchange throughout human history, connecting continents and shaping civilizations. The Atlantic's relatively young age means its seafloor is geologically active, with ongoing volcanism and spreading at the mid-ocean ridge. The rift that birthed this ocean is still widening at a pace of a few centimeters per year, a process that will continue for millions of years. The Atlantic is a testament to the restless motion of our planet's surface and the forces that continually reshape the world. The Indian Ocean has its own unique monsoon circulation. The Indian Ocean is the third largest ocean and is distinguished by its powerful seasonal monsoon winds that reverse direction twice a year. During the summer, warm, moist air rises over the Asian continent, drawing in humid ocean air that brings heavy rains to India and Southeast Asia. In winter, the pattern reverses, with dry air flowing outward from the continent. These monsoon cycles have shaped human civilization for millennia, influencing agriculture, trade, and cultural practices across the region. The Indian Ocean is also home to unique ecosystems, including coral reefs, mangroves, and a rich diversity of marine life. Warm waters year-round support some of the most productive fisheries on Earth. The ocean's circulation is intimately connected to global climate patterns, linking the tropics with the polar regions through the global conveyor belt. The Southern Ocean encircles Antarctica with endless currents. Flowing uninterrupted around Antarctica, the Southern Ocean is the only ocean that completely encircles a continent. Its most powerful feature is the Antarctic Circumpolar Current, the largest current on Earth, which flows eastward and connects the Atlantic, Pacific, and Indian Oceans. This current isolates Antarctica from warmer waters to the north, helping maintain the continent's ice sheets. The Southern Ocean is home to abundant krill, the foundation of a food web that supports penguins, seals, whales, and seabirds. Its waters are among the coldest and stormiest on the planet, with fierce winds and towering waves. Despite its harsh conditions, the Southern Ocean is incredibly productive, supporting some of the richest marine ecosystems on Earth. The endless loop of currents around Antarctica plays a crucial role in regulating global climate. The Arctic Ocean is covered by shifting sea ice that changes with the seasons. The Arctic Ocean is the smallest and shallowest of the world's oceans, lying beneath a cap of sea ice that waxes and wanes with the seasons. In winter, ice covers most of the Arctic, forming a frozen landscape traversed by polar bears and seals. In summer, portions of this ice melt, opening up shipping routes and exposing waters that have been locked away for months. The ice itself is constantly moving, driven by winds and currents, creating a dynamic mosaic of flows, ridges, and open leads. Climate change has accelerated the loss of Arctic sea ice, with summer coverage shrinking dramatically over recent decades. This decline has profound implications for wildlife, indigenous communities, and global climate. The Arctic Ocean's frozen surface is a barometer of planetary change, reflecting the health of Earth's climate system. Deep sea pressure can crush submarines designed for shallower depths. For every 10 meters of ocean depth, pressure increases by roughly 1 atmosphere, the equivalent of the entire weight of the air above us, at sea level pressing down. At the bottom of the Mariana Trench, pressure exceeds 1,000 atmospheres, more than enough to crush any conventional submarine like a soda can in an instant. Building vessels capable of withstanding such forces requires specialized engineering, thick titanium hulls, and carefully designed spherical compartments that distribute stress evenly. Even small weaknesses in seals or materials can lead to catastrophic implosion, with devastating consequences for any crew aboard. The few submersibles designed for extreme depths are marvels of engineering, able to descend where no other human-made vehicle can survive. The pressure gradient of the ocean creates a physical barrier as formidable as any on Earth, limiting exploration to the most advanced technology. The deep sea is a realm where the rules of surface life simply do not apply. Some creatures thrive in pressures that would destroy human-made machines. While crushing pressures would implode most engineered structures, deep-sea organisms have evolved bodies perfectly adapted to their environment. Their cells often contain special molecules that prevent proteins from being deformed by pressure, and their tissues are largely filled with incompressible water rather than air. Fish like the snailfish have been found at depths exceeding 8,000 meters, thriving where almost no other vertebrate can survive. Invertebrates like amphipods scavenge on the abyssal plains, seemingly unaffected by conditions that would be instantly lethal to surface dwellers. These creatures are products of millions of years of evolution, their biochemistry fine-tuned to cope with extremes. Studying them has provided insights into the limits of life and the adaptability of biological systems. What crushes steel is mere background for these remarkable animals. Life exists in complete darkness at the bottom of the ocean. Below about 1,000 meters, sunlight cannot penetrate, and the ocean is plunged into perpetual night that stretches to the deepest trenches. Yet life not only exists in this darkness, but thrives in remarkable abundance and diversity. Creatures here have evolved extraordinary adaptations, from bioluminescence to highly sensitive eyes capable of detecting the faintest glimmers, or no eyes at all. Food is scarce compared to the sunlit surface, so many animals have slow metabolisms, and can survive long periods between meals, sometimes years. Organic debris drifting down from above, known as marine snow, provides a trickle of nutrition to the depths. Hydrothermal vents and cold seeps offer alternative energy sources, supporting oases of life in an otherwise barren environment that challenge our assumptions. The deep sea challenges our assumptions about where and how life can exist on our planet. Darkness is no barrier to survival for those who have adapted to call it home. Hydrothermal vents support entire ecosystems powered by chemistry. Discovered in 1977, hydrothermal vents are fissures in the seafloor, where geothermally heated water erupts into the cold ocean depths. The water emerging from these vents is rich in dissolved minerals and chemicals, including hydrogen sulfide, which is toxic to most life. Yet around these vents, thriving communities of bacteria, tube worms, clams, crabs, and other organisms have evolved to exploit this chemical energy. The process is called chemosynthesis, a form of energy production that does not rely on sunlight. These ecosystems overturn the assumption that all life on Earth depends on photosynthesis. Hydrothermal vents showed that life can flourish in conditions once thought completely inhospitable. They also raised intriguing possibilities for life existing on other worlds, such as the ocean moons of Jupiter and Saturn. Bacteria near vents convert minerals into energy without sunlight. Chemosynthetic bacteria are the foundation of hydrothermal vent ecosystems, harvesting energy from the oxidation of chemicals like hydrogen sulfide, rather than from sunlight. These microbes form thick mats on surfaces around the vents and live symbiotically within the tissues of larger organisms, such as tube worms and clams. By converting inorganic chemicals into organic matter, they provide food for the entire vent community. This process is fundamentally different from photosynthesis and represents an alternative pathway for life to flourish. The discovery of chemosynthesis expanded our understanding of the energy sources available to life on Earth. It also suggested that similar processes could occur on other planets or moons, with volcanic activity and liquid water. These tiny bacteria are the unsung architects of one of the ocean's most extraordinary ecosystems. Giant tube worms can grow taller than a person near these vents. One of the most iconic inhabitants of hydrothermal vent ecosystems is the giant tube worm, known scientifically as Riftia pachyptilla. These worms can grow over 2 meters in length, their bright red plumes waving gently in the warm currents near the vent. Unlike most animals, tube worms have no mouth, gut, or anus. Instead, they rely entirely on symbiotic bacteria housed within their tissues to produce food from vent chemicals. The worms absorb hydrogen sulfide and oxygen through their plumes and transport these to the bacteria, which in turn provide nutrients back to the host. This partnership allows tube worms to thrive in an environment that would be lethal to most other organisms. Their rapid growth rate, among the fastest known for invertebrates, reflects the abundant energy available near vents. Giant tube worms are living monuments to the power of symbiosis. Some vent organisms thrive in temperatures hot enough to melt lead. Water emerging from hydrothermal vents can exceed 300 degrees Celsius, kept from boiling only by the immense pressure of the deep ocean. Surprisingly, life exists remarkably close to these superheated plumes. Certain bacteria and archaea, known as hyperthermophiles, can survive and even reproduce at temperatures above 100 degrees Celsius. Larger organisms like worms and shrimp cluster at the edges of the hot zones, where temperatures are cooler, but still far warmer than most marine environments. The ability of these organisms to tolerate extreme heat has provided insights into the biochemical limits of life. Proteins and cell membranes in these creatures are specially adapted to remain stable under conditions that would denature most biological molecules. Life at the vents challenges our notions of what is habitable. Other creatures live in water cold enough to freeze skin instantly. At the opposite extreme from hydrothermal vents, the deep ocean and polar seas are among the coldest environments on Earth. Temperatures near the ocean floor often hover just above freezing, and in polar regions, seawater can drop below 0 degrees Celsius without freezing due to its salt content. Creatures living in these conditions have evolved remarkable adaptations to cope with the cold. Fish in Antarctic waters produce antifreeze proteins that prevent ice crystals from forming in their blood. Invertebrates slow their metabolisms to conserve energy, sometimes going months between meals. The cold slows decay, meaning carcasses on the seafloor can persist for years, providing sustained food sources. Life in the frigid depths demonstrates the extraordinary resilience of biology in the face of punishing conditions. Antarctic fish produce natural antifreeze proteins in their blood. The waters around Antarctica are so cold that most fish would freeze solid within minutes, yet Antarctic icefish thrive in these frigid seas. Their secret lies in specialized antifreeze glycoproteins that circulate in their blood and tissues. These molecules bind to tiny ice crystals and prevent them from growing larger, effectively stopping the freezing process before it can cause harm. The evolution of these proteins is a remarkable example of adaptation to extreme environments. Some icefish have even lost their hemoglobin, relying instead on directly dissolved oxygen in their blood, which carries more efficiently in the cold. The study of antifreeze proteins has inspired applications in food preservation, medicine, and industry. Antarctic fish are living laboratories for understanding how life can persist at the edge of frozen oblivion. Bioluminescence allows many sea creatures to produce their own light. In the darkness of the deep ocean, the ability to produce light is a powerful adaptation that has evolved countless times. Bioluminescence, the chemical generation of light within living organisms, is found in a remarkable variety of marine life across all depths. Jellyfish, squid, fish, crustaceans, and even bacteria can emit glows ranging from soft blue-green to red, depending on their chemistry. The light is produced when a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase, releasing photons. Different species use bioluminescence for different purposes: attracting mates, luring prey, confusing predators, or communicating with one another across the darkness. Some creatures produce flashes to startle attackers, while others glow steadily to camouflage their silhouettes against faint surface light from above. Bioluminescence turns the deep sea into a living light show, a realm of glowing trails and flashing signals hidden from the sunlit world above. More than 90% of deep-sea creatures can glow. Studies of organisms captured from the deep ocean suggest that the vast majority are capable of producing light. This remarkable prevalence makes bioluminescence the rule rather than the exception in the abyss. The reasons for such widespread light production are varied, from finding mates in the darkness to confusing predators and luring prey. Because sunlight does not reach these depths, producing one's own illumination offers a significant advantage. The deep sea is often described as the largest habitat on Earth, and if most of its inhabitants are luminescent, then bioluminescence is one of the most common biological features on the planet. The diversity of light-producing mechanisms, involving different chemicals and structures, suggests that bioluminescence has evolved independently many times. The deep ocean is not a realm of darkness, so much as a realm of living lights. Some creatures use light to attract prey in the darkness. In the pitch-black depths far from any sunlight, a glowing lure can be irresistible to hungry organisms searching desperately for food. The anglerfish is perhaps the most famous example, dangling a bioluminescent appendage above its gaping jaws to draw curious prey within striking distance. Other species produce glowing mucus or flashes of light that mimic the movements of small organisms, tricking predators or prey alike into approaching. The strategy of using light as bait is highly effective in an environment where any glimmer could signal a meal worth investigating. Some squid and fish have evolved complex light organs that can be switched on and off, allowing precise control over the lure's intensity. The arms race between predator and prey in the deep has produced an astonishing variety of luminescent tricks over millions of years. Light in the abyss is both beacon and trap, serving those who wield it wisely. Others use bioluminescence to camouflage themselves from below. Many midwater fish and squid produce light on their undersides to match the faint glow filtering down from the surface, a strategy known as counter-illumination. By adjusting the brightness and color of their ventral light organs, they can hide their silhouettes from predators lurking below. Without this camouflage, their dark bodies would stand out against the dim light above, making them easy targets. Counter-illumination, requires the animal to sense ambient light levels and precisely match its own output, a sophisticated feat of biological engineering. This technique is so effective that it has evolved independently in many groups of deep-sea animals. The ability to become invisible by glowing is one of the ocean's most elegant survival strategies. In the twilight zone, light is both weapon and shield. Anglerfish dangle glowing lures to attract unsuspecting victims. The anglerfish is an icon of the deep sea, instantly recognizable by the bioluminescent lure projecting from its forehead. This glowing appendage, called an esker, is home to symbiotic bacteria that produce the light. The fish waves its lure slowly in the darkness, mimicking the movements of a small shrimp or worm. When a curious prey item approaches the glow, the anglerfish strikes with astonishing speed, engulfing the victim in its oversized jaws lined with needle-like teeth. Different species of anglerfish have evolved lures of different shapes and brightnesses, fine-tuned to attract specific prey. The deep sea's most famous hunter is also one of its most bizarre, a testament to the strange paths evolution can take in the darkness. The anglerfish proves that in the abyss, light can be deadly. The fangtooth fish has teeth so large, they cannot fit inside its mouth. The fangtooth is one of the most fearsome-looking creatures in the deep sea, despite its relatively small size of around 15 centimeters. Its teeth are proportionally the largest of any fish, so long that special sockets in the upper jaw and brain case accommodate them when the mouth is closed. These formidable fangs help the fangtooth capture whatever prey it encounters in the nutrient-poor depths. Despite its terrifying appearance, the fangtooth is harmless to humans and spends its life in the perpetual darkness below 1,000 meters. Its body is covered in small, rough scales, and its large eyes suggest some reliance on dim light for navigation. The fangtooth's grotesque appearance is a reminder that survival in the deep favors function over form. Beauty in the abyss takes strange shapes indeed. Gulper eels can swallow prey larger than themselves. The gulper eel, also known as the pelican eel, has an enormous mouth that can open wide enough to engulf prey much larger than its own body with remarkable efficiency. Its jaws are loosely hinged, and its stomach can stretch to accommodate oversized meals, an adaptation perfectly suited for life in an environment where food is scarce and unpredictable. When the eel encounters a potential meal, it strikes quickly, expanding its mouth like a net and trapping the victim inside before it can escape. The rest of its body is relatively slender and tapers to a long, whip-like tail that aids in propulsion through the dark waters. Gulper eels are found at depths of several thousand meters, where opportunities to feed may come only rarely over weeks or months. Their bizarre anatomy allows them to make the most of any encounter with prey, no matter the size. In the deep ocean, flexibility and opportunism are the keys to survival in a world of scarcity. Some deep-sea fish are transparent as glass. In the twilight zone, where faint light still penetrates, many fish have evolved transparent or nearly invisible bodies as a form of camouflage. By allowing light to pass through their tissues, these creatures avoid casting a shadow that could reveal them to predators. Species like the glass squid and barrel-eye fish have bodies so clear that their internal organs are visible. Achieving transparency requires specialized tissues, thin layers of skin, and minimal pigmentation. Some transparent organisms position their few opaque organs, such as the gut, vertically to minimize their visible profile. This adaptation is most common at intermediate depths, where some light still filters down, but darkness has not yet become total. Transparency is one of the ocean's most elegant solutions to the problem of hiding in plain sight. Others have skin so black it absorbs nearly all light. At depths where even bioluminescent flashes could reveal a hiding animal, some fish have evolved ultra-black skin that absorbs more than 99% of incoming light. This extreme pigmentation makes them nearly invisible, even when illuminated by the glowing lures of predators. The blackness is achieved through specialized melanin-packed cells arranged in a way that traps photons, preventing reflection. Species like the ultra-black dragonfish use this camouflage to approach prey and avoid becoming prey themselves. The discovery of these ultra-black fish has inspired material scientists developing coatings for telescopes and cameras. In the abyss, where any glint could spell death, disappearing into the darkness is a matter of life and death. These fish are living shadows, vanishing into the void. The giant squid was once thought to be a myth. For centuries, sailors told tales of monstrous sea creatures with tentacles long enough to drag ships to their doom. Scientists dismissed these stories as exaggeration until physical evidence began to accumulate. Giant squid carcasses washed ashore, and their remains were found in the stomachs of sperm whales. The giant squid can grow to over 12 meters in length, with eyes the size of dinner plates, the largest in the animal kingdom. Despite its size, the giant squid remained elusive, with the first images of a live specimen in its natural habitat not captured until the 21st century. It inhabits depths of several hundred to over 1,000 meters, where it hunts fish and other squid. The giant squid's legend reminds us that the ocean still holds creatures that once seemed the stuff of fantasy. Myth and reality often meet in the deep. The colossal squid has eyes the size of dinner plates. Even larger than the giant squid in terms of mass, the colossal squid roams the Southern Ocean around Antarctica. Its eyes are among the largest of any animal, measuring up to 30 centimeters across. These enormous eyes are thought to detect the bioluminescent trails of predators, like sperm whales, in the dim light of the deep. The colossal squid is also equipped with rotating hooks on its tentacles, weapons used to grip struggling prey. Despite its impressive size and armament, this squid is still poorly understood, with most knowledge coming from specimens caught accidentally by fishing vessels. The colossal squid lives in the remote, cold waters of the deep Antarctic, making study extremely challenging. It is a reminder that giants still lurk in the least explored corners of our planet. The blue whale is the largest animal ever to live on Earth. No dinosaur, no ancient sea monster, no creature alive or extinct is known to have surpassed the blue whale in size, making it the undisputed giant of all time. Adults can reach over 30 meters in length and weigh more than 150 tons, a mass equivalent to dozens of elephants combined. Despite their immense bulk, blue whales feed almost exclusively on tiny shrimp-like creatures called krill, consuming several tons each day during the feeding season. Their hearts are the size of small cars, and their arteries are wide enough for a human to crawl through with room to spare. Blue whales communicate with low-frequency calls that can travel across entire ocean basins, allowing them to stay in touch over vast distances even when separated. Hunting nearly drove them to extinction in the 20th century, but international protections have allowed populations to slowly recover over recent decades. The blue whale is a living monument to the ocean's capacity for grandeur and a symbol of conservation success. A blue whale's heart is the size of a small car. The heart of a blue whale is a marvel of biological engineering, weighing roughly 400 kilograms and capable of pumping blood through a body the length of 3 school buses. Each beat sends around 200 liters of blood surging through arteries so large that a small child could swim through the largest ones. The heartbeat of a resting blue whale can be detected from several meters away with sensitive equipment. During deep dives, the whale slows its heart rate dramatically to conserve oxygen, sometimes to only a few beats per minute. This physiological flexibility allows the blue whale to spend extended periods beneath the surface while searching for krill. The sheer scale of the whale's circulatory system is a testament to the engineering challenges of being the largest animal on Earth. Each heartbeat is a quiet thunder within the sea. Whale songs can travel across entire ocean basins. The low-frequency calls of great whales like blues and fins can propagate for thousands of kilometers through the ocean, crossing continents beneath the waves. Sound travels much faster and farther in water than in air, and the deep sound channel, a layer of water at certain depths where sound waves are refracted back, acts as a natural waveguide. Before industrial shipping filled the seas with noise, a whale calling off the coast of South America could potentially be heard near Africa across the Atlantic. These songs are used for communication, mate attraction, and possibly navigation across the vast ocean expanse. The complexity of humpback whale songs, which change over time and are shared among populations, hints at sophisticated social behavior and cultural transmission. However, increasing ocean noise from ships and sonar is making it harder for whales to hear one another across great distances. The ocean soundscape, once dominated by whale song, is now a cacophony of human activity that threatens this ancient form of communication. Dolphins appear to have names for each other. Research has shown that bottlenose dolphins develop unique signature whistles that function much like names. Each dolphin creates its own whistle early in life and uses it to identify itself to others. When dolphins want to get the attention of a specific individual, they will mimic that individual's signature whistle, essentially calling the other by name. This ability suggests a level of social complexity and individual recognition that was once thought unique to humans. Dolphins live in fluid social groups where keeping track of relationships is important for cooperation and survival. Signature whistles allow them to maintain bonds, even when individuals are separated in murky water or over distance. The discovery of dolphin names has deepened our appreciation for the intelligence and social lives of these remarkable animals. Some whales can hold their breath for over 2 hours. Cuvier's beaked whale holds the record for the longest dive by a mammal, staying submerged for over 2 hours while hunting in the deep ocean. To accomplish this feat, the whale slows its heart rate, shunts blood away from non-essential organs, and relies on oxygen stored in its muscles rather than its lungs. These adaptations allow it to reach depths exceeding 2,000 meters where prey is abundant and competition scarce. The pressure at such depths would crush a human, but the whale's flexible ribcage and collapsible lungs are built to withstand it. Upon surfacing, the whale must spend considerable time breathing to replenish its oxygen stores before diving again. The ability to remain submerged for so long opens up a hunting ground inaccessible to most other predators. These deep diving champions are the ultimate breath holders of the animal kingdom. Sperm whale clicks are louder than a jet engine. The sperm whale produces the loudest sound of any animal on Earth, with clicks that can exceed 230 decibels. These clicks are used for echolocation, allowing the whale to navigate and hunt in the total darkness of the deep ocean. The sound is generated by a complex organ in the whale's massive head, which can account for up to a third of its body length. At close range, the intensity of these clicks could theoretically stun or even kill prey. Sperm whales use echolocation to locate giant squid and other deep-sea prey hundreds of meters below the surface. The power and precision of their sonar rivals any human-made technology. Each click is a sonic pulse sent into the abyss, returning echoes that paint a picture of the hidden world below. The largest daily migration on Earth happens in the ocean each night. Every evening, as the sun sets and darkness descends, billions of creatures begin a vertical journey from the deep ocean toward the surface in a massive synchronized movement. This diel vertical migration involves zooplankton, fish, squid, and jellyfish, rising hundreds of meters to feed on phytoplankton and other surface organisms under cover of darkness. At dawn, they descend again to escape predators and the harmful effects of sunlight, completing their daily cycle. The scale of this migration is staggering, involving more biomass than any terrestrial migration, including the famous wildebeest herds of Africa. The movement of so many organisms transports nutrients and carbon from surface waters to the deep, playing a critical role in ocean chemistry and the global carbon cycle. This nightly journey connects the sunlit zone with the abyssal depths in a living conveyor belt that spans the entire ocean. The ocean breathes with this daily rhythm, pulsing with billions of travelers moving through the dark waters each night. Billions of creatures rise toward the surface as darkness falls. As the light fades from the sky, a vast army of marine life ascends through the water column. Tiny copepods, shrimp-like krill, lanternfish, and many other species make the upward journey each night to feed in the productive surface waters. They travel anywhere from a few dozen meters to over 1,000, depending on the species and local conditions. This coordinated movement is driven by the need to eat, while minimizing the risk of being eaten. Darkness provides cover from visual predators. The energy expended in these migrations is immense, but the reward is access to the ocean's most abundant food sources. When dawn approaches, the migrants descend once more, carrying the nutrients they consumed back into the deep. This nocturnal commute is one of the planet's most remarkable but least visible natural phenomena. Jellyfish have drifted through the oceans for over 500 million years. Jellyfish are among the oldest multicellular animals on Earth, with fossil evidence dating back more than 500 million years to the earliest ages of complex life. They appeared long before the dinosaurs, before fish developed jaws, and before life had colonized the land with plants and animals. Their simple body plan, essentially a bell of tissue propelled by pulsing contractions, has proven remarkably durable through mass extinctions and changing climates. Despite lacking brains, hearts, or blood, jellyfish have thrived across every ocean, and at every depth, from surface to abyss. Their success lies in their efficiency and adaptability, able to reproduce rapidly when conditions are right, and to survive on very little when food is scarce. Some scientists suspect that warming and polluted oceans may favor jellyfish blooms in the future, giving them an advantage over other species. These ancient drifters are survivors par excellence, outlasting nearly every other lineage on Earth through 500 million years of upheaval. One species of jellyfish may be biologically immortal. Turritopsis dohrnii, often called the immortal jellyfish, has the remarkable ability to revert from its mature adult stage back to its juvenile polyp form. When stressed by injury, disease, or old age, it can transform its cells, essentially resetting its life cycle and starting again. This process can theoretically repeat indefinitely, making the jellyfish biologically immortal, in the sense that it can avoid dying of old age. Of course, it can still be eaten, killed by disease, or destroyed by environmental factors. The discovery of this jellyfish has intrigued scientists studying aging and regeneration, offering insights into how cells can be reprogrammed. Whether this ability could ever be applied to other organisms remains speculative. The immortal jellyfish is a living example of how the ocean can challenge our assumptions about life and death. The Portuguese man of war is not a single creature but a colony. Often mistaken for a jellyfish, the Portuguese man-of-war is actually a siphonophore, a colonial organism made up of many specialized individuals called zooids. Each zooid is genetically identical, but differentiated to perform specific functions. Some form the gas-filled float, others produce the long stinging tentacles, and still others are responsible for digestion or reproduction. Together they function as a single coordinated organism, drifting on the surface and trailing tentacles that can exceed 30 meters. The sting of a man-of-war is extremely painful to humans and can be dangerous. The float itself is a distinctive bluish-purple bladder that catches the wind like a sail. This division of labor within a single colonial body is a unique evolutionary solution to life in the open ocean. The man-of-war is a living demonstration of cooperation at its most fundamental level. Some fish can change their sex during their lifetime. Many species of reef fish, including wrasses, groupers, and parrotfish, have the ability to change sex as part of their normal life cycle. Some begin life as females and later become males, a process called protogeny, often triggered when the dominant male dies or is removed from the group. Others do the reverse, starting as males and becoming females as they mature. This flexibility allows fish populations to maintain optimal sex ratios for reproduction, regardless of which individuals survive or are lost to predation. The transformation involves both behavioral and physiological changes, including alterations in coloration, body size, and reproductive organs over days or weeks. Sex change in fish is not rare or abnormal, but a regular feature of many reef ecosystems around the world. This remarkable plasticity is yet another way that ocean life has adapted to maximize reproductive success in dynamic environments. Clownfish and their anemone partners depend on each other to survive. The relationship between clownfish and sea anemones is one of the ocean's most famous examples of mutualism, a partnership where both parties benefit. Clownfish live among the stinging tentacles of anemones, protected by a layer of mucus that prevents them from being harmed by the venom. In return, the clownfish defend the anemone from predators and parasites, and their movements help circulate water, bringing oxygen and nutrients to their host. The anemone's venomous tentacles provide the clownfish with a safe haven from larger fish that cannot tolerate the sting. This partnership is so tight that clownfish rarely venture far from their host anemone throughout their lives. The bond between these two species demonstrates how cooperation can benefit both parties in the competitive world of the reef. Each depends on the other in a dance of mutual survival that has evolved over millions of years. Sharks existed before trees appeared on land. Sharks have been patrolling the oceans for over 400 million years, making them older than the earliest trees, which appeared roughly 350 million years ago. The ancient ancestors of modern sharks swam alongside armored fish and giant sea scorpions long before dinosaurs walked the earth. Over time, sharks have survived multiple mass extinctions that wiped out the majority of other species. Their basic body plan, streamlined shape, cartilaginous skeleton, and rows of replaceable teeth has remained remarkably consistent across the ages. This longevity speaks to the effectiveness of their design and their ability to adapt to changing conditions. Today, there are more than 500 species of sharks occupying niches from coral reefs to the open ocean, and from tropical waters to polar seas. Sharks are living fossils, reminders of an ancient world beneath the waves. Some sharks can detect a single drop of blood from miles away. Sharks possess an extraordinary sense of smell, with olfactory organs that can detect chemical traces in the water at incredibly low concentrations. While the exact sensitivity varies by species, some sharks can sense blood, diluted to 1 part per million, or even less. This ability allows them to locate prey over great distances, following scent trails through the currents like hounds on a trail. Their nostrils are not used for breathing, but are dedicated entirely to sampling the water for chemical cues. Once a shark picks up a promising scent, it will often zigzag through the water to home in on the source. This sensory superpower helps sharks find food in the vast, featureless expanse of the open ocean. Their noses are among the most finely tuned chemical detectors in the animal kingdom. Certain shark species glow with bioluminescent light. While bioluminescence is common among deep-sea fish and invertebrates, it was only recently confirmed in sharks. Several species of lantern sharks and kitefin sharks produce a soft blue-green glow using specialized cells in their skin. The kitefin shark, found in the deep waters off New Zealand, is now known to be the largest bioluminescent vertebrate. This light is thought to serve as camouflage, matching the faint glow from above to hide the shark's silhouette from predators or prey below. Bioluminescence may also play a role in communication or recognition among individuals. The discovery of glowing sharks has added a new dimension to our understanding of these ancient predators. Even in a well-studied group like sharks, the ocean still holds surprises that challenge our assumptions about what is possible. The Greenland shark can live for more than 400 years. The Greenland shark is one of the longest-lived vertebrates on Earth, with some individuals estimated to be over 400 years old, making them older than many nations. These slow-moving sharks inhabit the cold waters of the North Atlantic and Arctic, where low temperatures and limited food may contribute to their extended lifespan. Their growth rate is exceptionally slow, and they may not reach sexual maturity until they are well over a century old, perhaps around 150 years. Scientists determined their age by examining the lens of the eye, which contains proteins laid down in infancy that can be carbon dated. The oldest Greenland sharks alive today were born centuries before the Industrial Revolution, swimming through waters our ancestors never explored. Their vast lifespans make them living witnesses to centuries of ocean change, carrying the history of the sea in their slow-beating hearts. The Greenland shark is a patient giant, drifting through the dark, cold waters at the slow pace of deep time, a relic of ages past. Hammerhead sharks have extraordinary stereo vision. The distinctive head shape of hammerhead sharks, with eyes positioned at the ends of wide, flattened extensions, provides remarkable visual advantages. By spacing their eyes far apart, hammerheads gain a wider field of view and enhanced depth perception compared to other sharks. This stereo vision helps them spot prey, including stingrays buried in the sand, with greater accuracy. The head shape also contains a large number of electroreceptors, sensory organs, that detect the weak electrical fields produced by living organisms. Hammerheads can sweep their heads across the seafloor like a metal detector, sensing hidden prey beneath the sand. Their unusual anatomy is not a curse, but a suite of adaptations finely tuned for hunting. The hammerhead's head is a masterpiece of evolutionary engineering. The megalodon once ruled the ancient seas before its extinction. Megalodon was a giant shark that lived from roughly 23 to 3 million years ago, growing to lengths that may have exceeded 15 meters. Its jaws were lined with serrated teeth the size of a human hand, ideal for slicing through the flesh of whales and other large marine mammals. Megalodon was likely the apex predator of its time, dominating the oceans with no rivals. Fossil teeth and vertebrae have been found on every continent, indicating a truly global range. Its extinction coincided with significant changes in ocean temperature and the decline of its prey. Despite its enormous size and fearsome reputation, Megalodon could not survive the environmental upheavals of the Pliocene. Its legacy lives on in the popular imagination and in the fossil record, a reminder of the ocean's capacity to produce giants. Living fossils like the coelacanth still swim in modern oceans. The coelacanth was thought to have gone extinct with the dinosaurs until a living specimen was discovered off the coast of South Africa in 1938. This fish belongs to an ancient lineage that dates back over 400 million years, making it one of the oldest known vertebrate forms. Its lobed fins move in a pattern reminiscent of walking, providing clues about how fish first ventured onto land. Coelacanths live in deep underwater caves and are rarely seen, contributing to their mysterious reputation. A second population was discovered near Indonesia in the 1990s, showing that these living fossils persist in scattered refugia around the world. The coelacanth's survival challenges the assumption that ancient forms must inevitably give way to modern ones. Some creatures simply endure, quietly persisting while the world changes around them. Some fish can walk on land using their fins. Mudskippers are remarkable fish that spend much of their lives out of water, using their muscular pectoral fins to crawl across mudflats and even climb onto rocks and mangrove roots. They breathe through their skin and the lining of their mouth and throat, provided they stay moist. Mudskippers can be found in coastal areas of the Indo-Pacific, where they hunt insects, defend territories, and court mates on land. Their eyes, mounted on stalks atop their heads, give them excellent vision above the waterline. This amphibious lifestyle is thought to resemble an early stage in the evolutionary transition from water to land. Other fish, like the walking catfish, can also move across land for short distances, though less gracefully. These walking fish are living demonstrations of evolution's experimentation with terrestrial life. Flying squid can launch themselves through the air to escape predators. Several species of squid, particularly in the family Omistrophidae, can propel themselves out of the water and glide through the air for distances of up to 50 meters or more. They achieve flight by jetting water at high speed to gain momentum, then spreading their fins and tentacles to act as wings that provide lift. This behavior is typically used to escape fast-swimming predators, like tuna, dolphins, and other marine hunters. While airborne, squid can reach speeds exceeding those of most fish in the water, giving them a crucial advantage in the race for survival. The ability to leave the sea, even briefly, gives flying squid an escape route unavailable to most marine creatures restricted to the water. Sailors have reported squid landing on decks after launching themselves from the waves during night voyages. These airborne cephalopods are proof that the ocean's surprises do not end at the water's surface, and that evolution finds ways to exploit every available environment. Coral reefs are built by billions of tiny animals over centuries. Coral reefs are among the most complex and biodiverse structures on Earth, yet they are constructed by tiny polyps no larger than a fingernail. Each polyp secretes a hard calcium carbonate skeleton, and over generations these skeletons accumulate to form the massive reef structures we see today. A single reef can take thousands of years to grow, with layers upon layers of ancient polyps forming the foundation. Corals also host symbiotic algae in their tissues, which provide them with nutrients through photosynthesis. This partnership allows corals to thrive in nutrient-poor tropical waters. Reefs provide shelter and food for an astonishing array of fish, invertebrates, and other organisms. The patient labor of countless tiny creatures has built underwater cities, that rival any on land. The Great Barrier Reef is visible from space. Stretching over 2,300 kilometers along the northeastern coast of Australia, the Great Barrier Reef is the largest coral reef system on Earth and one of the only living structures visible from orbit. It is so vast that astronauts can see its outline from orbit, a ribbon of turquoise and green against the deep blue sea below. The reef is composed of nearly 3,000 individual reef systems and hundreds of islands, forming a complex mosaic of habitats. It supports an incredible diversity of life, including over 1,500 species of fish, 6 species of sea turtle, and countless invertebrates that call it home. The Great Barrier Reef is a UNESCO World Heritage Site and a focus of intense conservation efforts aimed at preserving its unique ecosystem. Rising sea temperatures and ocean acidification threaten its future, making its protection a global priority for environmentalists and governments alike. This underwater wonder is a natural monument visible from beyond our atmosphere, a testament to the grandeur of ocean life. Coral reefs support about a quarter of all marine species. Despite covering less than 1% of the ocean floor, coral reefs are home to roughly 25% of all known marine species. This extraordinary biodiversity rivals that of tropical rainforests, earning reefs the nickname of rainforests of the sea. The complex three-dimensional structure of reefs provides countless niches where fish, invertebrates, and other organisms can find food, shelter, and breeding grounds. The intricate relationships between reef inhabitants, from cleaning stations where small fish remove parasites from larger ones, to the partnership between corals and their symbiotic algae, create a web of dependencies. Losing coral reefs would trigger a cascade of extinctions affecting species far beyond the reef itself. The health of coral reefs is therefore a bellwether for the health of the ocean as a whole. These underwater gardens are treasures of life, concentrated in a thin sliver of the sea. Some corals glow with brilliant colors under ultraviolet light. Many coral species contain fluorescent proteins that absorb ultraviolet or blue light and re-emit it as vibrant greens, oranges, reds, and yellows. Under a black light, these corals can glow with an intensity and variety of colors that seem almost otherworldly. The function of this fluorescence is still debated, with hypotheses ranging from photoprotection to attracting symbiotic algae or even deterring predators. The proteins responsible for coral fluorescence have become valuable tools in biomedical research, including the famous green fluorescent protein used to track gene expression and cellular processes. Some corals increase their fluorescence in response to stress, potentially serving as an early warning sign of bleaching. The glowing beauty of corals under ultraviolet light is a reminder of the hidden dimensions of reef life. Even in the shallows, there is more to see than meets the unaided eye. Coral skeletons can endure for thousands of years. When coral polyps die, their calcium carbonate skeletons remain, providing the foundation for new generations of coral to grow upon. Over millennia, this accumulation of dead skeletons can form massive reef structures hundreds of meters thick. Fossil coral reefs can be found far inland on continents, remnants of ancient seas that have long since vanished. Scientists drill into coral cores to study past climate conditions, reading the chemical signatures locked in the skeletons like tree rings. Some reef formations visible today have been growing continuously for tens of thousands of years. The durability of coral skeletons means that the death of living coral does not immediately erase the reef, but without new growth, the structure eventually erodes. Coral reefs are monuments built slowly over geological time, layers of life piled upon life. Coral polyps can clone themselves to expand the reef. Corals reproduce in two main ways: sexually, by releasing eggs and sperm into the water during mass spawning events, and asexually, by budding off genetically identical copies of themselves. This asexual reproduction allows a single polyp to expand into a colony of thousands, all sharing the same genes. The ability to clone means that corals can rapidly colonize suitable surfaces and recover from minor damage. However, genetic uniformity can also be a weakness, making entire colonies vulnerable to the same diseases or environmental stresses. Sexual reproduction introduces genetic diversity, which is essential for long-term adaptation. The balance between cloning and sexual reproduction shapes the resilience of reef ecosystems. Coral colonies are both individuals and communities, blurring the line between organism and population. Scientists discover thousands of new marine species every year. Despite centuries of exploration and cataloging, the ocean continues to yield new species at a remarkable rate that shows no sign of slowing. Each year, marine biologists describe thousands of organisms previously unknown to science, from tiny invertebrates to fish, crustaceans, and even the occasional large animal. Many discoveries come from the deep sea, coral reefs, and other remote or inaccessible habitats that have only recently become explorable. Advances in technology, including remotely operated vehicles and DNA analysis, have accelerated the pace of discovery dramatically. Some new species are found in museum collections, overlooked for decades until a specialist takes a closer look with modern techniques. The sheer diversity of marine life means that cataloging it all is a task that may never truly be complete. Each new species discovered adds another piece to the puzzle of ocean biodiversity and the story of life on Earth. 2/3 of marine species may still be unknown to science. Estimates suggest that the total number of species living in the ocean could be anywhere from several 100,000 to tens of millions, with most scientists agreeing that we have barely scratched the surface. If these estimates are correct, then the vast majority of marine life has yet to be described by scientists or given formal names. Much of this unknown diversity is concentrated among small invertebrates, microbes, and organisms living in the deep sea or buried in sediments. Even well-studied groups like fish continue to yield new species from remote locations every year. The gap between what we know and what remains to be discovered highlights how little we truly understand about the ocean's living systems. Every expedition brings the possibility of encountering something never before seen by human eyes. The ocean is the last great frontier of biological exploration on Earth, offering endless opportunities for discovery. The ocean floor holds more gold than all the mines on land. Dissolved in seawater and buried in sediments, the ocean contains vast quantities of gold, far exceeding all the gold ever mined on land. However, the concentration is so low, roughly a few parts per trillion, that extracting it is not economically feasible with current technology. Over geological time, metals have accumulated on the seafloor in the form of manganese nodules and other mineral deposits. These nodules contain valuable metals, including manganese, nickel, copper, and cobalt. Interest in deep-sea mining has grown as terrestrial ore deposits become depleted, though the environmental impacts remain a concern. The ocean's mineral wealth is a tantalizing treasure that may one day be tapped as technology advances. For now, the riches of the deep remain locked beneath the waves. Millions of shipwrecks rest on the seafloor around the world. From ancient wooden vessels to modern steel ships, the ocean floor is littered with the remains of countless wrecks spanning thousands of years of maritime history. Estimates suggest that millions of ships have sunk over the course of human history, many of which have never been found, despite extensive searches. Some wrecks lie in shallow coastal waters, accessible to recreational divers, while others rest at depths beyond the reach of divers or submersibles in the abyssal plains. Famous wrecks like the Titanic and the Bismarck have been located and explored, capturing public imagination, but the vast majority remain undiscovered. These underwater graveyards hold historical artifacts, sunken treasure, and clues to past events that historians and archaeologists seek to uncover. Over time, wrecks become artificial reefs, colonized by corals, sponges, and fish that transform tragedy into habitat. Each wreck is a time capsule, preserving a moment of maritime history for future generations to discover and study. Cold depths can preserve wrecks perfectly for centuries. Beneath the cold, dark waters of the deep ocean, the processes of decay are dramatically slowed. Low temperatures inhibit bacterial activity, and the absence of light prevents photodegradation. Shipwrecks that sink to great depths can remain remarkably intact for centuries, with iron hulls, wooden beams, and even personal belongings preserved as if time had stopped. The Titanic, lying over 3.5 kilometers down, still retains recognizable features more than a century after its sinking. In anoxic environments, where oxygen is absent, preservation can be even more complete. These conditions have allowed archaeologists to study ancient wrecks with a level of detail impossible on land. The deep ocean is a natural museum, keeping the past frozen in darkness. Sunken cities from ancient civilizations lie beneath the waves. Changes in sea level, earthquakes, and land subsidence have submerged entire cities over the millennia, preserving remnants of ancient cultures beneath the waters. The ancient Egyptian city of Heraklion, once a thriving port and gateway to the Nile, was swallowed by the Mediterranean and lay hidden for over 1,000 years before its rediscovery. Off the coast of Japan, mysterious stone structures near Yonaguni have sparked debate about whether they are natural formations or the remains of a lost civilization that predates recorded history. In the Mediterranean and Black Seas, submerged harbors, temples, and streets have been mapped by underwater archaeologists using the latest technology. These sunken cities offer glimpses into past ways of life and the forces that shaped human history, including the power of the sea itself. The ocean has claimed many of our ancestors' greatest works, yet it has also preserved them for future discovery in ways that land cannot match. Beneath the waves, history waits patiently to be found by those willing to look. The Bermuda Triangle has inspired centuries of mystery and legend. The Bermuda Triangle, a loosely defined region of the Atlantic between Miami, Bermuda, and Puerto Rico, has long been associated with unexplained disappearances of ships and aircraft. Stories of vanished vessels and mysterious forces have fueled countless books, films, and theories. However, investigations by insurers and coast guards have found that the rate of incidents in the Bermuda Triangle is not significantly higher than in other heavily traveled regions. Many disappearances can be attributed to sudden storms, navigational errors, and the challenges of the open ocean. The legend persists in part because of the area's busy shipping and aviation routes, which mean more opportunities for accidents. The Bermuda Triangle remains a potent symbol of the ocean's mystery, even if its supernatural reputation is exaggerated. The sea's power to inspire fear and wonder needs no paranormal explanation. Earth's magnetic field leaves stripes recorded on the ocean floor. As new oceanic crust forms at mid-ocean ridges, iron-rich minerals within the cooling lava align with the Earth's magnetic field before solidifying. When the planet's magnetic field reverses, as it has done many times over geological history, The stripes of magnetized rock on either side of the ridge record the flip. Scientists discovered this pattern in the 1960s, providing powerful evidence for seafloor spreading and plate tectonics. The magnetic stripes form a symmetrical pattern on either side of the ridge, like a barcode encoding the history of magnetic reversals. By matching these stripes with the known record of reversals, geologists can date the age of the ocean floor. This magnetic memory of the seabed has transformed our understanding of how continents move. The ocean floor is a giant tape recorder, slowly unspooling the story of our planet. Black smokers release mineral-rich fluids like underwater forges. Black smokers are a type of hydrothermal vent that spews superheated water laden with dissolved minerals, primarily sulfides of iron and copper, into the cold ocean depths. As this hot fluid meets the cold seawater, the minerals precipitate out, forming towering chimney structures that can reach heights of tens of meters over time. The dark color of the plume gives black smokers their name, creating the impression of underwater smokestacks billowing from the sea floor. The water emerging from black smokers can exceed 300 degrees Celsius, yet life thrives nearby, fueled by chemosynthetic bacteria that form the base of unique ecosystems. The minerals deposited around vents are of interest to mining companies, but extraction poses significant environmental risks to these fragile habitats. Black smokers are windows into the Earth's interior, where the planet's heat and chemistry spill out onto the seafloor in dramatic fashion. These underwater forges are among the most dramatic features hidden beneath the waves, connecting the deep ocean to the planet's molten core. The deep sea is the largest habitat on Earth. When measured by volume, the deep ocean, below 200 meters, constitutes more than 90% of the living space on our planet. This vast realm is characterized by darkness, cold, and crushing pressure, yet it supports a surprisingly diverse array of life. From the abyssal plains to the trenches, organisms have adapted to conditions that would be fatal to surface dwellers. The sheer size of this habitat means that even small average densities of life add up to enormous total biomass. Despite its importance, the deep sea remains one of the least explored environments on Earth. New species and ecosystems are discovered with nearly every expedition that ventures into this realm. The deep ocean is a reminder that most of our planet's living space lies hidden beneath the waves, waiting to be understood. Underwater landslides can trigger devastating tsunamis. Submarine landslides occur when unstable sediments on continental slopes or around volcanic islands suddenly collapse and slide into deeper water. The displacement of water can generate tsunamis that travel across ocean basins at high speed. Historical events like the landslide associated with the 1998 Papua New Guinea tsunami have demonstrated the destructive potential of these underwater collapses. The causes of submarine landslides include earthquakes, volcanic activity, and the gradual accumulation of sediments on steep slopes. Climate change may increase the risk by destabilizing frozen methane deposits and causing sediment layers to liquefy. Predicting and monitoring submarine landslides is difficult because they occur in remote, deep-water environments. These hidden collapses are among the ocean's most sudden and dangerous phenomena. The ocean holds vast reservoirs of frozen methane beneath the sea floor. Methane hydrates are ice-like structures in which methane molecules are trapped within a lattice of water molecules. They form under conditions of high pressure and low temperature, typically found in deep ocean sediments and beneath permafrost. The total amount of methane locked in these hydrates is estimated to exceed all other fossil fuel reserves combined. If disturbed by warming or pressure changes, hydrates can release their methane, a potent greenhouse gas. Sudden releases could accelerate climate change and destabilize the seafloor, triggering submarine landslides. Scientists are studying the stability of methane hydrates as part of efforts to understand and mitigate climate risks. The frozen methane beneath the ocean floor is both a potential energy source and a significant environmental concern that demands careful monitoring. Warming oceans could release this methane and accelerate climate change. As ocean temperatures rise, the stability of methane hydrates in shallow marine sediments and along continental margins is threatened. If warming waters destabilize these deposits, large quantities of methane could escape into the ocean and atmosphere. Methane is a far more potent greenhouse gas than carbon dioxide over short timescales, meaning even modest releases could have significant climate impacts. Past episodes of rapid warming in Earth's history have been linked to methane releases, suggesting the risk is not merely theoretical. Scientists are monitoring hydrate-bearing regions to detect early signs of destabilization. Preventing runaway methane emissions is one of the reasons limiting global warming is so urgent. The frozen methane beneath the ocean is a sleeping giant that could awaken with profound consequences. Sea levels have risen and fallen dramatically throughout Earth's history. Over geological time, sea levels have fluctuated by hundreds of meters in response to changes in climate, ice sheet volume, and tectonic activity. During ice ages, vast amounts of water were locked up in continental glaciers, and sea levels dropped, exposing land bridges and continental shelves. In warmer periods, ice melted and seas rose, inundating coastal areas and reshaping continents. Evidence of past sea levels can be found in ancient shorelines, coral terraces, and sedimentary rocks far from today's oceans. These natural fluctuations occurred over thousands to millions of years, giving ecosystems time to adapt. Today, human-driven climate change is causing sea levels to rise at an accelerating rate, much faster than natural cycles. Understanding past changes helps scientists predict what the future may hold. Melting ice sheets are causing sea levels to rise today. The Greenland and Antarctic ice sheets contain enough frozen water to raise global sea levels by many meters if they were to melt entirely. As the planet warms, both ice sheets are losing mass at accelerating rates, contributing to rising seas. Satellite measurements show that ice loss has more than tripled since the 1990s. The melting is caused by warming air temperatures, warmer ocean water undercutting glaciers from below, and changes in precipitation patterns. Even modest increases in sea level threaten low-lying coastal cities, islands, and ecosystems. The pace of future rise depends on how quickly humanity reduces greenhouse gas emissions. The ice sheets are responding to a warmer world, and their fate will shape coastlines for centuries to come. Some islands may disappear beneath rising waters in the coming decades. Low-lying island nations like Tuvalu, Kiribati, and the Maldives face an existential threat from rising sea levels. Even a rise of less than a meter could inundate much of their land, contaminating freshwater supplies and making agriculture impossible. Storm surges that once were rare could become frequent, eroding coastlines and destroying infrastructure. For the people of these islands, climate change is not a distant threat, but a present reality, reshaping their daily lives. Some communities are already planning for relocation, facing the prospect of becoming climate refugees. The disappearance of inhabited islands would be an unprecedented event in modern history. The fate of these nations is a stark warning about the consequences of unchecked warming. The ocean absorbs most of the excess heat from global warming. Since the Industrial Revolution, the ocean has absorbed more than 90% of the extra heat trapped by greenhouse gases. This buffering has slowed the warming of the atmosphere, but the heat does not disappear. It accumulates in the ocean, raising water temperatures at all depths. Warming seas expand, contributing to sea level rise, and can intensify storms by providing more energy to hurricanes and typhoons. Marine ecosystems are feeling the effects as species shift their ranges and coral reefs bleach. The heat stored in the ocean today will continue to influence climate for centuries, even if emissions are halted. The ocean's role as Earth's heat sink comes at a cost, measured in warming waters and stressed ecosystems. Our blue planet is absorbing the consequences of a warming world. Warming waters threaten coral reefs with mass bleaching events. When ocean temperatures rise even slightly above normal, the symbiotic algae that provide corals with nutrients and color can be expelled, leaving the coral white and stressed. This phenomenon, known as bleaching, can be reversed if temperatures return to normal quickly, but prolonged or repeated bleaching leads to coral death. Major bleaching events have struck reefs around the world with increasing frequency, including severe episodes on the Great Barrier Reef. The loss of coral affects not only the reef itself but the countless species that depend on it for food and shelter. Scientists are working on strategies to help reefs adapt, including selective breeding and assisted migration. However, the ultimate solution is reducing the warming that causes bleaching in the first place. Coral reefs are canaries in the coal mine for ocean health. Ocean acidification makes it harder for shellfish to build their shells. As the ocean absorbs carbon dioxide from the atmosphere, it becomes more acidic, lowering the pH of seawater. This acidification reduces the availability of carbonate ions, which are essential building blocks for the shells and skeletons of mollusks, corals, and many other marine organisms. Species like oysters, clams, and sea urchins may struggle to form and maintain their protective structures in more acidic waters. Laboratory studies and field observations have shown impaired growth and increased mortality in affected species. The effects ripple through the food web, threatening fisheries and ecosystems that depend on these organisms. Ocean acidification is sometimes called the other carbon dioxide problem, a hidden consequence of emissions that receives less attention than warming. The chemistry of the ocean is changing in ways that challenge life at its most fundamental level. Marine protected areas help ecosystems recover and thrive. Marine protected areas are zones where human activities are restricted to allow ecosystems to recover and biodiversity to flourish. Within these sanctuaries, fish populations can grow larger and more abundant, coral reefs can regenerate, and sensitive species can find refuge from overexploitation. Studies have shown that the benefits often spill over into surrounding waters, boosting fish catches for local communities and enhancing regional biodiversity. Protected areas can also serve as reference sites for scientists to study healthy ecosystems and compare them to impacted ones. Establishing and enforcing protected areas requires political will and community support, but the rewards can be substantial for both nature and people. The ocean's capacity for recovery, given the chance, is remarkable and offers hope for the future. Marine protected areas are investments in the long-term health of our seas. Plastic pollution has reached even the most remote ocean depths. Plastic debris has been found in the Mariana Trench, on uninhabited islands, and in the stomachs of animals living far from any human settlement. An estimated 8 million tons of plastic enter the ocean each year, breaking down into smaller and smaller pieces but never fully disappearing. Microplastics have been detected in seafood, salt, and even drinking water. The durability that makes plastic so useful also makes it a persistent pollutant, lasting for centuries in the environment. Marine animals can become entangled in larger debris or ingest plastic, often with fatal consequences. Addressing plastic pollution requires a combination of reducing production, improving waste management, and cleaning up existing debris. The ocean's plastic problem is a stark illustration of humanity's impact on even the most remote corners of the planet. Some creatures mistake plastic fragments for food with deadly consequences. Sea turtles often confuse floating plastic bags for jellyfish, their natural prey, swallowing them and suffering intestinal blockages. Seabirds feed plastic pellets to their chicks, who starve with stomachs full of indigestible material. Whales, fish, and filter feeders ingest microplastics along with their food, accumulating toxins in their tissues. The chemicals associated with plastics can disrupt hormones, impair reproduction, and weaken immune systems. The death toll from plastic ingestion is difficult to quantify, but is thought to affect millions of animals each year. Reducing the flow of plastic into the ocean is essential to protecting marine life. The tragic irony is that substances designed for human convenience are now killing creatures who have no use for them. The sound of the ocean is changing due to human activity. The ocean was once filled primarily with natural sounds, the songs of whales, the snapping of shrimp, the rumble of earthquakes, and the hiss of breaking waves against distant shores. Today, shipping, sonar, construction, and oil exploration add a cacophony of human-made noise that can drown out these natural rhythms. This acoustic pollution can travel for thousands of kilometers, interfering with the communication, navigation, and feeding of marine animals that depend on sound. Whales may be forced to sing louder or at different frequencies to be heard over the din, expending precious energy. Fish and invertebrates can be disoriented or stressed by sudden loud sounds that disrupt their normal behavior. Managing ocean noise is increasingly recognized as an important conservation challenge by scientists and policymakers. The soundscape of the sea is an invisible but vital dimension of marine ecosystems that deserves protection. Noise pollution affects marine mammals that rely on sound to communicate. Whales, dolphins, and seals use sound for virtually every aspect of their lives, from finding food to navigating, attracting mates, and maintaining social bonds. Anthropogenic noise from ships, seismic surveys, and military sonar can mask these critical signals, forcing animals to expend more energy to communicate or to fall silent entirely. In some cases, loud sounds have been linked to strandings and behavioral disruptions. The cumulative effect of chronic noise exposure on marine mammal populations is still being studied, but the concern is growing. Quieter ship designs and regulations on underwater noise are being developed to reduce the impact. The ocean's great communicators deserve waters where their voices can be heard. Silence, or at least quiet, is a form of habitat that marine mammals need. New exploration technologies are revealing secrets of the deep. Advances in remotely operated vehicles, autonomous underwater drones, and improved sonar systems are opening up the deep ocean to exploration as never before. High-definition cameras now transmit live video from the sea floor, allowing scientists and the public to witness discoveries in real time. DNA sampling techniques can identify organisms from water samples without ever capturing them. Improved batteries and materials are extending the range and duration of deep-sea missions. Satellite monitoring helps track ocean conditions on a global scale, providing context for what is found below. Each new technology brings with it the possibility of finding species, ecosystems, and geological features never before seen by human eyes. The ocean's secrets are being unlocked one innovation at a time. Autonomous submarines can now reach places humans cannot. Autonomous underwater vehicles, or AUVs, are transforming ocean exploration by venturing into environments too deep, too remote, or too dangerous for crewed submersibles. These robotic explorers can spend days or weeks at sea, mapping the seafloor, collecting samples and recording data without risking human lives. Some AUVs are designed to navigate under ice shelves, others to descend into deep trenches, and still others to survey vast stretches of open ocean. Their sensors can detect everything from temperature and salinity to the presence of specific chemicals or organisms. Data from AUVs have contributed to discoveries of hydrothermal vents, shipwrecks, and previously unknown species. As artificial intelligence improves, these vehicles will become even more capable and autonomous. The robots of the deep are our scouts into the unknown. Every expedition to the deep brings discoveries that rewrite what we know. The history of deep-sea exploration is a catalogue of surprises that have repeatedly overturned scientific assumptions. When scientists first reached hydrothermal vents, they found thriving ecosystems where none were expected, powered by chemistry rather than sunlight. Bioluminescence turned out to be far more widespread than anyone imagined, with the majority of deep-sea creatures capable of producing light. Creatures thought to be extinct for millions of years have been found alive and well in the darkness of the abyss. Each dive, each survey, each sample collected has the potential to overturn assumptions and expand our understanding of life's possibilities. The deep ocean is a reminder that the world is larger and stranger than our textbooks suggest, constantly revealing new wonders. What we think we know is always provisional, subject to revision, with the next discovery waiting in the depths. The ocean remains one of Earth's last great frontiers of exploration. Despite centuries of sailing, diving, and scientific investigation, the ocean is still largely unexplored and full of mysteries waiting to be solved. More of the moon's surface has been mapped in high resolution than the seafloor that lies just kilometers beneath our ships. Vast areas of the deep ocean have never been visited by humans or their machines, holding secrets we cannot yet imagine. Each expedition brings the possibility of encountering new species, undiscovered ecosystems, and geological wonders that reshape our understanding. The ocean's mysteries are not diminishing as we explore. Rather, each answer raises new questions that drive further inquiry. In an age when satellites can photograph every corner of the land, the deep sea remains genuinely unknown and genuinely wild. It is a frontier not in the past but in the present, waiting for the next generation of explorers to venture into its depths. The ocean invites curiosity and rewards those who dare to discover its secrets. And now the quiet wonders of the ocean begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the vast blue world that covers most of our planet. From sunlit surface waters teeming with life, to the crushing darkness of the deepest trenches. From volcanic vents where life thrives without sunlight, to ancient sharks that patrolled these waters before the first trees grew on land. You have explored how the ocean shapes our climate, produces the air we breathe, and holds mysteries we are only beginning to understand. You have learned that beneath the calm surface lies a world of underwater mountains, hidden valleys, glowing creatures, and secrets waiting to be discovered. You are connected to this story more deeply than you may realize. Right now, as you listen, the ocean is quietly circling the globe, carrying warmth from the tropics toward the poles, producing oxygen and sustaining the rhythm of life on Earth. The water in your body was once part of this endless blue. The breath you take carries the gift of the sea. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle pulse of waves against a distant shore, like the slow rise and fall of the tides under the watchful moon. Tonight, as you rest, the ocean continues its timeless work. Currents will flow through the darkness. Creatures will rise toward the surface and descend again. Volcanic vents will feed strange ecosystems in the eternal night. And somewhere in the deep, discoveries are waiting for future explorers to find. You are a small, warm presence within this vast blue world, peacefully resting among the wonders. Sleep well, sweet dreams. And may you carry with you the quiet knowledge that beneath every wave and within every drop, the ocean holds stories older than memory itself. Thank you for joining me on this journey through the mysteries of the deep. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the wonders that surround us. There are more wonders waiting, more secrets hidden in the depths, more gentle truths to drift through on quiet evenings. Rest well, and may the endless rhythm of the ocean keep you company through the night. This has been Drowsy Discovery. Good night.